Bismillahirrahmanirrahim. Assalamualaikum dan selamat sejahtera. Okey, ini adalah slideshow for chapter 4, which is continuity and Bernoulli equation. So in this chapter we will go through continuity and Bernoulli equations and how to apply both equations in solving fluid flow problems. Okay, right. So in this section we will discuss on the determining the continuity for frictionless flow, its definitions and also equation related. Okay, macam kita tengok sini continuity, alright, and frictionless flow. Frictionless flow means that tak ada friction lah. Kita consider the flow is steady and ideal. Okay, it's not like an actual flow. Okay, the relationship, dan kita akan juga tengok relationship between pressure, velocity and stagnation pressure. Okay, and then lastly kita akan understand the use and limitation of the Bernoulli equation and apply it to solve a variety of fluid flow problems. So untuk apply this Bernoulli equation pun dia ada assumption yang kita kena take note before kita nak apply. Okay, dia ada limitation dia lah sebenarnya untuk Bernoulli equations ni. And then based on both equation ni, both important equation ni, kita akan guna dua-dua untuk selesaikan masalah related to any fluid flow problems lah. Basically. Okay, first of all kita go through the continuity equation. So what is a continuity equation? So based on the mathematical expression, it is the principle of conservation of mass. So means that the mass is conserved. Okay, contohnya kalau kita ada satu pipes ni kan, mass flow rate yang masuk dekat inlet sini must be equal to mass flow rate yang keluar dekat outlet. Okay, for a control volume that has a single inlet and outlet, the conservation of mass states that for a steady flow, kita consider steady flow, the mass flow rate into the volume must be equal to the mass of flow rate out. Okay, so contohnya kan, ini adalah satu area yang mana kita ada B in and B out, flow in and flow out lah. Okay, so and then kita create satu area yang dinamakan control volume. So area yang kita akan consider adalah this area, yang mana kita akan tengok apa yang masuk kat sini adalah sama dengan apa yang keluar kat sini. So based on this continuity, the mass flow rate into the volume, to this control volume, must be equal to the mass flow rate out at the outlet. Okay, so based on continuity equation, for this situation is expressed by is either volume flow rate A times V, delta T is a true time lah. Okay, and dekat ni maksud dia macam dekat area 1 and dekat area 2. Okay, so volume flow rate and at inlet and volume flow rate at the outlet. Okay, so for for those yang related to mass, kita ada additional terms here, which is the density that we need to apply. Okay, so the differences between the volume flow rate and the mass flow rate is this density. Okay, so samalah konsep dia. Kita tahu mass equals to density time volume. So in order to get mass, kita kena darabkan density ke atas volume. Senang kan nak tengok perbezaan dia kat sini. So based on continuity, what's the mass flow rates in equals to mass flow rate out. So means that rho A dekat position 1 ni, row A1 V1 equals to row A2 V2. But usually fluid flow yang masuk dengan fluid flow yang keluar adalah fluid flow yang sama. So density is usually can be ignored. So usually kita akan dapat A1 V1 equal to A2 V2. Okay, but this is, as I said, usually boleh juga terjadi yang masuk tu adalah water, yang keluar tu adalah apa, vaporize kan, gas ke something kan, sebab dia ada heated elements dekat in the middle, mana dah tahu kan. So dia kalau macam tu kita kena consider different density lah dekat situ. Okay, so now we go for some example lah, sebab continuity ni senang je sebenarnya. Okay, what's go in sama dengan apa yang keluar juga. So a piping system that has a Y configuration. Okay, dia kata kat sini Y configuration for separating the flow. Okay, so kita consider saya lukis sikit lah, Y Y set. Nak kena tahu juga yang mana inlet yang mana outlet kan. So the diameter of the inlet given the diameter of the inlet is 12 cm and the diameter of the outlet are 8 cm and 10 cm. So kita tahulah inlet dia satu, outlet dia dua. So kita consider dari atas inlet dia 12 cm. Terbesar pula, tak apalah. Okay, and then dia ada Y satu keluar dekat 10 cm, satu lagi keluar dekat 8 cm. So yang ni consider diameter 1 12 cm ataupun equivalent tu 12 kali 10 kuasa negatif 2 meter. Yang ni 8 kali 10 kuasa negatif 2 meter. And the last one is 10 times 10 to the power of minus 2 meter. So yang ni kira diameter 1, ini kiranya diameter 2, ini kiranya diameter 3. So what else the question give? Okay, the velocity in the 10 cm leg is 20 meter per second. So dekat sini dia bagi V, yang ni V3 lah equals to 20 meter per second. And then what else? The mass flow rate at the inlet is 200 kg per second. So kita tahu dekat sini M1 equals to 200 kg per second. Okay, given that the density of the water is 1000 kg per meter cube. So given that rho water untuk case ni constant kilogram per meter cube. So the question asks determine the velocity out at the 8 cm pipe section. So the question asks untuk kita dapatkan this V2 dekat sini. Okay, so macam mana kita nak start? So firstly kita kena refer kepada continuity tadi lah kan. Apa dia kata? The mass flow rate into the volume must equal to the mass flow rate out. So apa yang masuk dekat sini mesti sama juga dengan apa yang keluar dekat sini. Okay. So kita tahu total mass flow rate in must be equals to total mass flow rate out. So mass flow rate in kita ada apa? Satu je kan, inlet dia satu je. So kita ada M1 equals to, yang keluar kita ada dua. So kita ada M2 plus M3 kan. Tapi sekarang kita basically kita nak cari dekat V2 kan. So kita buat M2 lah kat kiri equals to M3 minus M1. Okay, so apa ni, M3 ni sekejap, apa saya buat silap, sorry matematik pun dah tak betul. Okay, sorry So kita tak tahu M2 is actually M1 minus M3 lah kan, sebab M3 ni kita bawa ke sana kan. Okay, so M1 is given 200 kg per second. Okay, tolak M3 ni macam mana? M3 ni rho A1 B1 lah. Okay, so 200 minus rho is given 1000. Area is pi r squared lah. Pi r squared untuk apa? Sorry, yang ni dekat 3 lah, B3 Dekat A3 ni dia bagi apa? Diameter dia equivalent to diameter dia, sorry yang ni diameter ni. Okay, diameter dia equivalent to 10 cm. So the radius is bagi 2 lah. So adalah 5 kali 10 kuasa negatif 2 square kan, pi r square kan. Okay, V3 given 20. Okay, so ini akan jadi 200 minus, kita kena kira sikit, okay, so 200 minus 157, around lah 1.557. So this will be 43 kilogram per second. Okay, so kita tahu sekarang mass flow rate yang keluar dekat channel 2 ni, outlet number 2 ni adalah 43 kg per second. But the question asks for velocity V2. So kita tahu mass flow rate at 2 equals to rho A2 V2. So V2 equals to mass flow rate at 2 over rho A2. So mass flow rate at 2 kita tahu dah 43 kan, divide by density is 1000 and area dekat 2 ni adalah pi r squared kan. R dia adalah 4 kali 10 kuasa negatif 2 square, and this will give sekejap kan, okay, V2 kita akan dapat around 8.55 meter per second. Okay, and mudah kan? Mudah aja. The concept of continuity. Apa yang mass flow rate in equals to mass flow rate out. Sama juga lah, volume flow rate in equals to volume flow rate out. Tak kisahlah sebenarnya sama ada dia kata volume ataupun mass, since if let's say the density is, the fluid flow density is sama, yang ni dengan ni sama aja sebenarnya, sebab kita akan consider A1 B1 equals to A2 B2. Okay, Bernoulli's equation. So we talk about Bernoulli's equation. I think you guys might have pernah dengar kan sebelum ni, especially those yang ambil physics subject during the SPM. So bila kita cakap pasal Bernoulli, what comes first in our mind, and what comes first in apa yang kita dapat fikirkan? Okay, first of all, it is related to the relation between pressure and velocity. So bila kita kata Bernoulli, mesti ada kena-mengena dengan P and V. So bila pressure naik, velocity turun, and bila velocity naik and pressure turun kan. So that is the relation, satu naik, satu mesti turun, and that is the basic concept when we talk about Bernoulli's equation. And this Bernoulli equation is also one of the most important equation in fluid mechanics bila kita deal dengan fluid that is in motion, bila fluid tengah bergerak. Okay, application of Bernoulli is one of the most important, and also it is also can be considered as one of the most simplified equation as well, and but it only work if certain parameters is fulfilled. Okay, in order for us to apply those Bernoulli equation, we must make sure that certain parameters or assumption is fulfilled. If not, the Bernoulli's equation will be invalid. Okay, so when we talk about the assumption, what are the assumptions that we need to make on the fluid motion so that we can apply this Bernoulli equation? So first of all, the fluid must be inviscid. Okay, actually I have already explained to you what is the differences between viscous flow and those inviscid flow. Okay, it's okay, I will remind you lagi sekali. What is this inviscid flow? Inviscid flow is when the viscosity in the fluid flow is neglected. Means that there will be no shear stress. Kan last time saya cakap mengenai viscous versus inviscid. When we talk about viscous is those related dengan viscosity. So meaning kita akan consider viscosity dalam fluid flow. However, for inviscid kita consider no viscosity. And so means that for viscous kita kalau kita consider flow in pipes, bentuk dia akan jadi macam ni. Okay, this is the velocity lah. Velocity kat tengah dia adalah Umax, maximum velocity, tapi dekat surface kita ada zero, velocity equals to zero, and this is due to the fluid viscosity. Okay, so however for the inviscid kita consider there are no viscosity, thus the velocity is the same throughout the pipes. Okay, semua ni adalah Umax. Okay, so in order for us to apply the Bernoulli equations, we must make sure that this condition is applied. Okay, secondly, kita kena consider juga the fluid flow must be steady. Means that if let's say the fluid flow is steady, there will be no change of velocity with time. That is why dv over dt must be equal to 0. Okay, so means that if let's say dalam satu-satu pipe tu, kita consider pipes cases A and B, velocity no velocity changes happen. Okay, alright. Thirdly, kita kena consider juga if the fluid in motion must be incompressible. And bila kita cakap incompressible, macam mana tu? Incompressible adalah fluid flow with yang tak boleh compress, tak boleh compress. So apa contoh fluid yang tak boleh dikompres? Yang biasa kita tengok adalah macam water ataupun liquid lah. Liquid kita tak boleh compress kan, ataupun sometimes gases but with low velocity. Okay, gases with low velocity ni kita boleh define through Mach number. Mach number pun saya dah define last time kan. Mach number equals to V over C. V is the velocity of the fluid and C is the speed of sound. So if let's say Mach number is more than 0.3, the fluid flow is considered compressible. Okay, however, if let's say Mach number is less than 0.3, then we can assume that the flow is incompressible. Okay, so logic kan? So means that if let's say low velocity, means that V value must be very low lah. So that is why bila Mach rendah ataupun Mach less than 0.3, it can be considered as incompressible. But if let's say this velocity is tinggi, it will result Mach number more than 0.3, then we can assume that the flow is incompressible. So these are the important assumptions that we need to take into account if let's say we want to apply the Bernoulli equations. Okay, the fluid must be inviscid, and the flow must be steady, and the flow must be also incompressible. Okay. Okay, so now we go details into the Bernoulli equation. What is the Bernoulli equations? So this is the energy equation of an ideal flow along streamline. Okay, along streamline for energy equation. So untuk ni dia guna Euler's description. So actually maybe saya kena terangkan sikit. There are basically two ways in describing fluid in motion. In motion. So kita boleh describe dalam dua sistem, sama ada Langrerian description ataupun Eulerian description. Okay, so kalau kat sini diguna Eulerian description. So basically in describing fluid in motion ni, these are the two system yang kita boleh apply ataupun description. So what is the differences between Langrerian and this Eulerian? So for a moving fluid, first of all, for the Langrerian, Langrerian contoh macam fluid flow. So kita ambil satu point. You can pick a single particle dalam fluid yang tengah bergerak tu, and we follow where it goes. Itu maksud dia bila kita guna Langrerian description. Contoh macam fluid flow dalam satu pipe tu, kita ambil satu particle and kita follow macam mana fluid motion based on that particle movement. That is bila kita refer to this Langrerian description. However, if let's say kita guna this Eulerian description, kita consider macam kita stay in one place, okay, and then in one place tu kita dah set ada boundary, ada inlet and outlet, and then kita buat, kita simply observe what happens in that particular volume, okay, that you have created. Okay, that is this description based on Eulerian. So tahu perbezaan antara Langrerian and Eulerian. Langrerian kita follow that particle. However, for Eulerian kita dah set satu box, ada inlet, ada outlet, lepas tu kita observe what happens in that particular volume, apa yang terjadi kepada fluid motion. So in the end, it doesn't really matter if let's say kita guna yang mana-mana pun, sama ada Langrerian ke Eulerian ke, it doesn't matter to use which system, because in the end you are still tracking the same fluid, so the result will be the same. Okay, that is enough I think for description on fluid motion. Okay, so Euler's equation, the equation of motion of an inviscid fluid along a streamline for a steady flow with gravity as the only body force, can be written as, apa yang kita kena consider is velocity, pressure, and also height based on gravity lah. Okay, so application of a force through a distance ds along a streamline would physically imply work interaction, and therefore an equation for conservation of energy along a streamline can be obtained by integrating this equation with respect to ds. Okay, so kita kena integrate this equation with respect to ds, the distance. Okay, so bila kita integrate, sekejap saya padam sikit dekat sini. Okay, so kita integrate each of this term in 4.1 with ds. So bila kita integrate, actually kita akan dapat potong benda ni, potong benda ni, potong benda ni kan. So dia akan jadi integrate of v dv equals to minus integration of 1 over rho dp minus integration of g dz. Okay, so kita integrate v dv, kita akan dapat v squared over 2 equals to, yang ni kita akan dapat p over, sorry ada negatif kat sini, p over density minus zg, ataupun kita bawa semua ke kiri, v square over 2 equals to sorry, not equals to, akan jadi plus pressure over density plus zg equals to constant. So this is a very important equation that we need to know ataupun memorize atau whatsoever lah untuk this chapter, because all the calculation will involve this basic equations ataupun Bernoulli's equation lah. Okay, so actually this is the same thing lah. Okay, so where C yang kita letak dekat bahagian kanan ni is actually a constant lah, a constant along a streamline. In case of an incompressible flow, kita akan write benda macam ni lah, sama macam yang saya derive tadi lah. Okay, so this equation 4.2 and 4.3 are based on the assumption that no work or heat interaction between a fluid element and the surrounding takes place. So means that the flow macam tu je, dia tak ada additional heat ataupun work yang applied to the fluid flow surrounding. So it can be considered that the flow is natural. The first term of the equation 4.3 represent the flow work per unit mass. Okay, this one it can be considered as the flow work per unit mass, and the second terms, which is this one, can be considered as the kinetic energy per unit mass. Okay, and the third term is the potential energy. Okay, so yang ni selalunya kita tak perlu hafal, kita pakai logik lah kan. Bila kita kata work, mesti ada related to pressure kan. So bila kita kata kinetic energy, mesti ada kena-mengena dengan V squared kan, velocity squared. And lastly, bila kita kata pasal potential energy, it must be related to altitude. Okay, dia ada Z term kat situ. Okay, so therefore the sum of these three terms in the left hand side of equation this 4.3 can be considered as a total mechanical energy per unit mass. Okay, per unit mass which remains constant along a streamline for a steady, inviscid and incompressible flow of fluid. And macam assumptions that we have to make earlier. In order for us to apply the Bernoulli equation, the flow must be steady, inviscid and incompressible. Hence, this equation is also known as the mechanical energy equation. Okay, so back into history, the equation itself, it was developed by Daniel Bernoulli in 1738 and is therefore referred to as a Bernoulli equation. So the Bernoulli equation takes from the creator's name lah. Okay, Daniel Bernoulli. Each term in equation 4.3 has the dimension of energy per unit mass. Okay, so macam kita cakap tadi kan, The first term is flow work per unit mass. The second one is the kinetic energy per unit mass, and the third one is the potential energy per unit mass. Kita dapat tengok semua ni adalah total mechanical energy per unit mass. Okay. The equation, however, the equation can also be expressed in terms of energy per unit weight. And how to convert this is by, macam mana? Kita divide each term by rho g. Okay, divide by rho g, divide by rho g, divide by rho g. So kita akan dapat P over rho g, V squared over this one kita potong lah, kita dapat 2g, and then Z plus Z equals to C1. So in a fluid flow, the energy per unit weight is termed as heat. So dia terbalik dari tadi Okay, accordingly equation 4.4 can be interpreted as the first term is pressure head, dan sebelum ni kalau dalam mass dia adalah work per unit flow work per unit mass kan. So kalau dalam weight kita panggil dia pressure head, and then the second term is the velocity head, and the third term is the potential head, which is equal to the total head or total energy per unit weight. So berbeza tadi, ini if in terms of mass, this one is in terms of head. Okay. And Bernoulli's equation provides the relationship between pressure and velocity, of course, and also the elevation along a streamline. Kan? So macam tadi P over rho g plus V squared over 2g plus Z equals to C. So yang ni kan, bila kita go through lama-lama, kita akan terhafal terus sebenarnya tau. Okay, so apa dia kata tadi? Bernoulli equation provide the relationship between pressure, velocity and elevation along a streamline, kan? Betul kan? So benda ni tak perlu hafal, kita tengok kan, the first term ada relate to pressure, the second term ada relate to velocity, and the third term ada related to the elevation along a streamline, and it can be applied to solve simple problems such as flow from a tank, so or flow under a sluice gate, or flow through a nozzle, and etc. So ini adalah contoh if let's say kita nak apply Bernoulli's equation between point 1 and point 2 kita consider position 1 and position 2. Okay. Ini seperti yang saya terangkan tadi lah. So this is very important the equation assumptions that need to be applied in deriving the Bernoulli's the study must be steady, incompressible, inviscid, and this is the additional lah. It is flowing along a streamline lah, or it can be considered as a continuous flow. Okay, so untuk this part, this is related to the modified form of a Bernoulli equation where we need to consider a heat loss. Okay, so the derivation of mechanical energy equation for a real fluid so yang ni kita consider a real fluid sebab bila kita kata Bernoulli equations banyak assumption yang kita perlu buat, tapi in reality it is not a real fluid kan. Bila kita consider tak ada the inviscid flow tak ada viscosity, itu semua, most of the usually all fluid flow mesti ada viscosity. Okay, so for a real fluid depends much on the information about the frictional work. Okay, mesti ada frictional work done by a moving fluid element and is excluded from the scope of the book. Okay, however, in many practical situations, problem related to real fluid can be analysed with the help of modified form of Bernoulli equation. Kalau kita tengok sini, ini bila kita nak consider Bernoulli equation between point 1 and point 2. However, kita tambah satu lagi term HF, in which it represent the frictional work done, which is also can be considered as the work done against the fluid friction per unit weight of a fluid element while moving from position 1 to position to position 2, okay, along a streamline. This term HF ni is usually referred as a head loss, kan, macam cakap tadi, head loss. This head loss between point 1 and 2, since it amounts the loss in total mechanical energy per unit weight between point 1 and 2 on a streamline due to the effect of fluid friction or viscosity. Macam saya cakap tadi, mesti in real fluid mesti dia ada fluid friction or viscosity. Dia tak akan jadi perfect punya fluid macam kita apply Bernoulli sebelum ni, kan. It physically signifies that the difference in the total mechanical energy between station 1 and 2 is dissipated, okay, into intermolecular or thermal energy, and is expressed as loss of heat. And the terms loss is conventionally symbolized as HL instead of HF in dealing with practical problems. So it doesn't matter lah. Sometimes it can be considered as HF and sometimes it can be considered as HL, okay. And for an inviscid flow, HL equal to 0 lah, kan. Kalau kita consider inviscid, kita no viscous, HL equal to 0, and the total energy is constant along streamline. But if let's say for a real fluid, kita kena consider this additional head loss punya terms, okay. Okay, so now we proceed dengan items yang berkaitan dengan Bernoulli equations. Bila kita cakap pasal Bernoulli, macam saya mentioned, it must be related to pressure, velocity, and also one additional items, which are the stagnation pressure. So from this part onwards, kita akan fokus kepada details of the Bernoulli equations, which consider the pressure and the velocity, and also some part of stagnation pressure. What is stagnation pressure? But before we proceed, kita kena tahu the basic concept is that total pressure, P total, would be equal to PS plus PD. Okay, this is the basic concept, which means T is actually total, which is total pressure, and then PS is static pressure, okay, and PD is a dynamic pressure. Okay, so total pressure is equivalent to the static pressure plus the dynamic pressure. So firstly, the concept of static pressure. The thermodynamic or hydrostatic pressure caused by molecular collision is known as the static pressure. In a fluid flow, as is usually referred to as the pressure P. So usually, kalau in this case kita consider as a hydrostatic lah, which means that the fluid is adalah water ataupun fluid lah, and that's why it is called the hydrostatic. And then when the fluid is at rest, this pressure is the same in all direction and is categorically known as the hydrostatic pressure. Okay, so by definition itself, kita tahu static is something that is not moving. So if the fluid is at rest, the pressure yang ada pada satu-satu molekul tu adalah sama in all directions, and this pressure is actually called the static or hydrostatic pressure. and the static pressure is a parameter to describe the state of a flowing fluid lah. If let's say static pressure ni hanya beri if let's say pressure yang adalah pressure yang dikenakan ke atas molekul tu sendiri, and dynamic is the pressure yang dikenakan when it is moving lah. Okay, so the concept of a static pressure, in order for us to investigate or to estimate the static pressure is by using this measurement. Firstly, kita boleh guna single wall tap, this one, ataupun kita boleh guna this multiple wall tap. Okay, so macam the wall tap here kan, kalau kita tengok kan, if a hole is made at the wall kan, dia ada hole kat sini and is connected to any pressure measuring device. Kat sini lah kita akan letak apa-apa measuring device, it will sense the static pressure at the wall. Okay, static pressure at the wall, selalu static pressure dekat sini actually sama juga dengan static pressure dekat mana-mana lah kan. And the type of hole at the wall is known as the wall tap. Okay, this is what is known as a wall tap. The fact that a wall tap actually senses the static pressure can be appreciated by noticing that there is no component velocity along the axis of the hole. So dekat sini maksud dia tak that particle is not actually moving lah. That is why it can be considered those pressure here as a static pressure. Okay, kita kena create wall tap, a hole, untuk kita dapatkan the value of static pressure. So in practice, instead of a single wall tap, a number of taps along the periphery of the wall are made and are mutually connected by flexible tubes. So kita juga boleh guna this multiple wall tap untuk calculate the static pressure, but mostly kita akan guna this wall tap lah. Okay, and then the concept of hydrodynamic, static and total pressure. So yang ni adalah contoh yang diberi untuk kita lebih faham lah kewujudan this static and dynamic pressure ataupun hydrostatic and this hydrodynamic pressure. So let us consider a fluid that is flowing through a pipe. So kiranya yang ni diconsider yang ni this is the pipe. Okay, a pipe with varying cross section area, and considering 2 points A and B, A dekat sini and B dekat sini okay, such that A and B are at height ZA and ZB. Okay, ada ZA, ZB, VA, VB and PA and PB. Alright, if we consider the fluid to be stationary, then change of pressure which it will result in negative rho g, where the subscript HS represent the hydrostatic case. Macam kita cakap when the fluid is at rest ataupun fluid to be stationary, kita boleh consider the pressure exists is the static pressure ataupun hydrostatic punya case, which will represent by HS. So bila kita kata fluid is stationary, kita tak guna Bernoulli equation, kita guna rumus asal kita tahu pressure equals to F over A, and then F kita represent mg over A, and then mass kita tahu kan, jisim ketumpatan or density equals to mass over volume. So kita replace mass equals to rho v kat sini times g over A, and then kita bukakan lagi, kita tahu kan volume equals to width kali length kali h, and then kita tahu area equals to width kali length je kan. So potong kita tinggal h, that is why dekat sini tinggal h je. Okay, tak apa, saya tunjuk sikit. So maksud dia rho times W LH times G over W times L. So potong kita hanya tinggal rho HG. That is why kita ada rho H is the elevation lah. So sometimes kita guna Z. So ZB minus ZA. Okay, so this is the equation obtained if let's say the fluid is not moving. If we want to calculate the pressure difference between point A and point B, but the fluid is not moving, this is the equation that we need to use. Okay, where PAHS is the hydrostatic pressure at point A and PBHS is the hydrostatic pressure at point B. Okay, and thus from the equation we can conclude that hydrostatic pressure at a point in the fluid is the pressure acting at the point when the fluid is at rest, or pressure at the point due to weight of the fluid above it. Okay, because it is not moving. Okay, pressure yang ada adalah pressure yang dikenakan antara intermolecular of the fluid itself yang tengah rest, ataupun due to weight of the fluid atas dia, sebab dia tak bergerak kan. So apa yang dikenakan pressure kat situ adalah force yang sesama molekular ataupun weight yang dikenakan due to gravity. Okay, now if we consider the fluid to be moving, sekarang kita consider fluid yang moving pula. The pressure at a point can be written as a sum of two components, which are the hydrostatic and hydrodynamic. Macam yang saya mention awal-awal tadi kan, total pressure equals to dynamic pressure plus the static pressure. So in this case is a hydrodynamic pressure plus the hydrostatic pressure. Okay, so by using the Bernoulli equation between points A and point B, so kita nak consider macam actually case ni lah, kita take this case, but this time around the fluid is moving. So apa kita kena buat adalah kita kena guna Bernoulli equation. Bernoulli equation kita tahu P over rho G plus V square over 2G plus Z equals to C, and then actually kita akan dapat this equation. Macam mana kita dapat this equation? Okay, saya akan tunjuk sikit. So kita tahu Bernoulli apa? Bernoulli, based on Bernoulli's rumus dia P over rho G plus V squared over 2G plus Z equals to C. Betul tak? Okay, so kita tahu P ni if P total kan, so in actual dia ada dua. So kita ada P A due to hydrostatic plus P A due to hydrodynamic over rho G plus V squared A ni point A rho G plus ZA equals to PB hydrostatic plus PB hydrodynamic over rho G plus VB squared over 2G plus ZB. Okay, this is at point A. Sekejap, saya tukar balik sikit. Point A, this is at point B. Okay, so kita gabungkan. Okay, macam kita nak gabung PAHS plus PAHD minus PBHS minus PBHD over rho G. Velocity kita bawa ke kanan, so on the left hand side kita hanya ada the elevation ZA, ZB pergi sana, dia jadi minus ZB. Okay, yang ni satu parts equal to PBHS plus no yang ni kita dah bawa, kita hanya ada velocity belah kanan kan. So kita ada VB squared minus VA squared over 2G. Okay, so dekat sini actually kita boleh gabungkan which one is hydrodynamic and which one is hydrostatic. So kita buat PAHD minus PBHD over rho G okay, plus PA hydrostatic minus PB hydrostatic over rho G plus ZA minus Z. Macam mana tulis Z ni pun. Okay, ZB equals to, yang ni kita tulis balik lah, right hand side ni, square over 2G. Okay, so sama tak? Kan? So kita ada hydrodynamic at point A minus hydrodynamic at point B. Okay, lepas tu kita ada hydrostatic at point A minus hydrostatic at point B. Okay, this one. Lepas tu kita ada ZA minus ZB. Okay, and then kita ada VB squared minus VA squared. VB squared minus VA squared. So kita dapat tahu this is actually based on Bernoulli. Macam mana kita nak kaitkan situation between point A and point B. Okay, so this is apa yang kita boleh guna pakai. Okay, so actually kita boleh, based on this equation, kita boleh simplify lagi based on this from equation 4.2. Which one is equation 4.2? Ingat tak lagi? Adalah this one, kan? Ini terjadi apabila kita consider hydrostatic case. Okay, kan? HS P at point A, HS minus PB at point HS equals to rho G ZB minus ZA. Okay. So from equation 4.2, the term within the square bracket cancel each other out. So maksud dia, kat kawasan ni kita boleh potong disebabkan based on this equation. Okay, so ini dia kata apa? Saya copy copy, saya letak dekat sini. Keluar tak? Sekejap. Oh, tak keluar pula. Sekejap, saya tarik sekali lagi. This one, and then saya paste dekat sini. Okay, so ini yang diberi, kan? Okay, so actually kita tahu P, pen, sekejap. Sekejap, ini pun saya padam sekejap. Okay, so saya tukar colour. Since PA minus PBH, kita bawa yang ni ke sini, PAHS minus PBHS. Rho G ni kita bawa ke kiri over rho G equals to apa? ZB minus ZA. Okay, so because benda ni dengan benda ni sama, kita boleh cancel out these two part. Okay, that is why in the end kita hanya tinggal dengan this and this, which is this and this on the hydrodynamic part sahaja. Okay. Okay, so untuk equation 4.6 ni dia tak buat apa, dia just rearrange sahaja, and dia bawa everything ke kiri, which is on the right hand side. Kita boleh consider dia ada constant. So at point A and point B here, pressure plus velocity term, pressure plus velocity term at point A and point B equals to this constant. Equation 4.5 and 4.6 convey the following, which is the pressure at the location has both hydrostatic and hydrodynamic components. Betul kan? Sebab kita dah kira tadi kan, kita ada PHS dengan PHD, and the difference in kinetic energy arises due to hydrodynamic components only. So this is based on here. So macam kita cakap sebelum ni kan, this V is related to the kinetic energy. So bila kita tengok this kinetic energy, dia hanya bergantung kepada hydrodynamic components only. Kalau kita tengok on the left here. Okay. So in a frictionless flow yang tak ada friction macam dia consider in viscous lah, the sum of flow work due to hydrodynamic pressure and kinetic energy can be considered conserved, sebab tak ada loss. Bila tak ada friction, maksud dia tak ada loss lah kan. So that's why dia conserve. Such conservation shall apply to the entire flow field if the flow is irrotational. Maksudnya dia just streamline je lah, dia bergerak tanpa dia rotate. And then the hydrodynamic component is often called the static pressure, and the velocity term dynamic pressure. The sum of two PO and this one is also known as a total pressure. Okay. Okay. This part is velocity at the point using a pitot tube. Actually kan, bila kita kata pasal Bernoulli, this part always I keep on repeating. Kita bila kita kata pasal Bernoulli, mesti ada related to pressure and velocity, kan? So for this part, actually with a combination of both piezometer and pitot tube, kita boleh obtain the velocity at a specific point. Contohnya, kita akan dapat kira static pressure bila kita guna piezometer. Okey, macam kita tahu, macam explanation yang saya cakap sebelum ni, bila kita kata pasal static pressure ni adalah pressure due to benda tu yang tak boleh gerak. Contohnya kalau kat sini kan, piezometer ni digunakan untuk kira static at point 1 ni. So maksud dia dekat sini dia akan dapat the value of static pressure. And the second one, which is the pitot tube. Pitot tube pula digunakan untuk measure the stagnation pressure. Stagnation pressure dekat sini. So this is the first time kan you guys dapat pasal diperkenalkan dengan stagnation pressure. So what is actually a stagnation pressure? So the stagnation pressure is the pressure when the flow has a stagnation velocity or V equals to 0. So kita consider macam dekat point ni, okay, dia nak sampai sini, dia akan dikenakan satu pressure yang sangat tinggi, yang mana velocity dia akan jadi 0, kan? Macam the concept of Bernoulli itself lah. Bila P increase, V decrease kan. So bila V kosong, P is at its max. Betul tak? Kan? So same condition applied here, dekat tip of this pitot tube. So by perfectly aligning the pitot tube with the flow will come to a stop at the tip of the pitot tube, hence providing the stagnation pressure measurement. So kita kena align this pitot tube dengan flow direction, kan? So flow direction, kalau kita tengok ni horizontally like this, and then kita align with the pitot tube. So dekat tip of this pitot tube, actually the flow will stop. Bila flow stop, means that velocity equals to 0. Bila velocity equals to 0, P equals to P stagnation. Pressure di mana velocity is 0. Okay. And by applying the Bernoulli equations between point 1 and point 2, kita dapat this equation. Ingat lagi, kita tulis banyak kali P over rho G plus V squared over 2G plus Z equals to constant kan. Okay, so yang ni antara point 1 dengan point 2. So P1 over rho G plus V2 squared over 2G plus yang ni 1 1 equals to P2 over rho G plus V2 squared over 2G plus Z2. Okay, but since there are no elevation kan. Point 1 and point 2 ni ketinggian dia sama, betul tak? They are on the same elevation. So since they are equal, we can cancel it out. Okay, so rho G ni kita bawa ke atas. So P1 plus kat sini dia jadi rho V squared over 2. Okay, V1 equals to P2 plus rho V2 squared over 2. Okay, so ini yang kita boleh gunakan. Okay, so sama kan dengan ni, P1 rho V1 squared over 2, P2 rho V2 squared over 2. So in the end kita just manipulate from the Bernoulli equation sahaja untuk capai apa-apa maklumat penting yang kita nak dapat. So dari sini kita tahu kita boleh dapatkan pressure kat sini, velocity sini, pressure sini, velocity sini. Apa P1, apa V1, apa P2, apa V2. Betul tak? Okay, so next kita dah dapat this equation, but kita tahu kan dekat tip of this pitted tube velocity is 0 and P equals to the P stagnation kan. So P2 adalah P stagnation lah, and then this V2 equals to 0. So kita tahu kat sini V2 equals to 0, so this term is cancelled. So apa yang kita tinggal hanya P1 plus rho V1 squared over 2 equals to P2. Kita rearrange supaya kita dapat this value. Okay, then kita boleh dapat the value of velocity at point 1. Flow dia berapa dia bergerak dalam these pipes. And then where P1 and P2, the value of P1 and P2 ni actually are known from the height of the fluid column in the piezometer and pitted tube. P1 kita dapat dari piezometer kan, daripada P static, and then pitted tube daripada P2 kan kat sini. So maksud dia ketinggian ni, ini kita boleh dapat untuk P1, ini kita boleh dapat daripada P2 kan. Dan kita boleh dapat the value of velocity P1. Ni contoh Okay, so this is a bit more details on the explanation about the stagnation pressure. So a stagnation pressure at a point in the fluid flow is actually the pressure which could result in the fluid were brought to rest isentropically kan. So stagnation pressure at a point bila pressure which could result in fluid were brought to rest. Contohnya dekat gambar ni, kalau kita tengok gambar ni, saya ambil colour lain sikit. Okay, contoh yang ni flow over a vehicle So a stagnation appear actually at this point, point A, di mana dia kena direct impact dekat kereta tu. So this is actually the stagnation pressure. Okay, in which the flow of the fluid were brought to rest, and it says here isentropically. So the word isentropically implies the sense that all the entire kinetic energy of a fluid particle is utilized to increase its pressure only. That is why at this point PS is max, and sebab semua kinetic energy daripada flow yang sebelum impact ni dah convert kepada pressure. Okay, that is why all the kinetic energy parts on V square over 2 kan, dalam Bernoulli tu dia dah convert kepada stagnation pressure kan. Macam kita cakap, energy cannot be destroyed, but it can convert into other energy kan. That is Newton law kan. So this is possible only in a reversible adiabatic process known as the isentropic process. So bila kita cakap pasal flow over a vehicle, actually macam-macam benda yang terjadi kan. Seronok sebenarnya study pasal fluid flow ni. So this is actually an example of a fluid flow over a vehicle. Memang kita, kalau untuk this part kita hanya tahu pasal this stagnation pressure sahaja. Actually flow tu tak berhenti kat sini je. flow yang lain-lain akan bergerak, dia akan ada separation, and then dia akan create those separation bubbles depends on the shape of the car, and then dia akan ada part di mana flow yang dah separate tu dia akan reattach balik, and then dia akan separate balik dekat sini, and then they will create the separation bubble, and then dia ada wake dekat sini. So this is bila kita sembang pasal aerodynamics of vehicle lah, kan, di mana it creates region of flow separation and reattachment, and then all this separation bubble will cause the drag to increase, in which result or affect the performance of a car. So yang tu just additional knowledge for you guys lah. So actually untuk this part saya nak intensify dekat bahagian stagnation pressure kat sini aje lah. So actually gambar yang belah kanan ni contoh lah yang boleh refer So kalau tak silap yang ni adalah pressure contour. Yang ni the second one is a velocity contour. Contour ni adalah gambar yang yang colored surroundings yang belakang dia. Okay, so if let's say kita refer to the first figure here, kita ada vehicle ni tengah bergerak, and then this pressure occurs due to the flow impact on the vehicle. Macam saya cakap tadi kan, dekat area flow to impact dengan the vehicle, kita dapat lihat the pressure is very high, kan. Kita dapat tengok kat sini color merah. This is due to the effect of this stagnation pressure lah, kan. Those yang kena direct impact akan ada high pressure. So kat kawasan high pressure ni actually bila kita tengok gambar yang sama, dia akan ada very low velocity. Yang ni yang kita apply the concept of Bernoulli. Bila pressure increase, velocity mesti decrease. Dekat area yang mana pressure paling tinggi, velocity mesti paling rendah. Contoh macam kat belakang ni kan. Kat belakang ni pressure tinggi, so velocity rendah. So ini adalah wake yang occur. Okay, ni just additional knowledge lah about aerodynamics of vehicle. So ni contoh untuk pengiraan of stagnation pressure lah. So let us consider the flow of fluid through a closed passage. So yang ni satu closed passage. Okay, and then at section 11, okay, let the velocity and static pressure of the fluid be uniform. So dekat sini yang color biru ni, kita consider the flow is incompressible. Okay, sebab daripada gambar tu sendiri kan, dia tak ada boundary layer, dia tak ada effect of friction or whatsoever kan, viscosity kan. So kita consider the incompressible, in which the velocity and the static pressure is uniform kan. Kita nampak velocity and static pressure is uniform. And then consider a point A dekat sini. Okay, at that section just in front of which at right angle tube with one end facing the flows and one end other end is closed kan, untuk di mana dia akan bertemu satu right angle, this right angle tube in which satu part dia face this flows, satu part lagi dia face di pressure measuring device or enclosed. Okay, so what is actually happen? So when equilibrium is attained, bila satu-satu equilibrium dah capai, the fluid in the tube will be at rest. Kan, contoh macam dekat sini dah penuh sangat, dalam ni dah penuh, so dia akan capai satu equilibrium di mana fluid yang dalam this tube akan rest, tak bergerak. Okay, and the pressure at any point in the tube including the point B will be more than that at A where the flow velocity exists. So means that dalam B ni fluid dah tak bergerak, so pressure dia sangat tinggi dan pressure dekat sini is actually more, pressure kat sini is actually more than pressure dekat sini, yang mana flow tu tengah bergerak kan, ada velocity exist. So by the application of Bernoulli equation between point A and point B, in consideration of the flow to be inviscid and incompressible kan, ni incompressible and inviscid lah macam saya cakap tadi okay, we have this P naught equals to P plus PV square over 2. Since ni kita tak ada elevation kan, so kita consider plus Z tu tak adalah. Okay, so where P and V, this P and V actually are the pressure and velocity respectively at point A. Okay, P and V dekat sini, and P naught is actually the pressure at B. Okay, P naught ni pressure dekat B ni according to the in which according to the definition refers to stagnation pressure at point A. Okay, so ini is actually equivalent to stagnation. Okay, alright, so it is found from this equation 4.7 ni that the stagnation pressure P naught ni, this stagnation pressure consists of two terms, which is the static pressure and the dynamic pressure kan. Saya tulis balik lah, P naught equals to P plus rho V squared over 2, in which this term is also known as the static pressure. This part is the dynamic pressure. Actually benda ni pun kita boleh fikir secara logik lah kan. Static pressure adalah pressure yang tak bergerak, so dia ada hanya P. Bila dynamic pressure adalah pressure yang bergerak, in which kita kena consider velocity of the fluid lah. And then we rearrange so that kita boleh dapat what is the velocity. Kita just rearrange this equation kepada ini untuk dapatkan value of velocity at point A. And therefore it appears from equation 4.8 that from a measurement of both static and stagnation pressure, kita boleh dapatkan the value of velocity. Okay, this one lah. And but in real life, it is actually difficult sebenarnya untuk kira this stagnation pressure, because real fluid actually contain friction kan. Kita anggap sebelum ni benda tu perfect kan. Fluid flow kalau kita tengok kan, tak ada boundary layer kan, elok je, no viscous effect kan. Fluid tu inviscid kita consider, but in real life dia ada friction. Okay, the pressure in the stagnation tube indicated by any pressure measuring device for example will always be less than PO kan. In actual, P real would be much lower than the exact PO, P naught, since a part of the kinetic energy will be converted into intermolecular energy due to fluid friction. Okay, semua kinetic energy macam saya cakap tadi kan, bila stagnation pressure, all the kinetic energy yang fluid particle tu bergerak, dia akan convert to stagnation pressure. But in real life, actually tak semua kinetic energy tu akan di-convert kepada pressure, akan ada yang loss due to friction. Okay, and this is actually can be considered by taken care by including this empirical factor dekat depan ni, satu constant in determining the velocity. Okay, so this is additional factor that need to be considered if let's say kita consider a real fluid lah, in which frictions takes place. Okay, so in the end kita boleh conclude that P stagnation is equivalent to this. Okay, whereby this is the stagnation pressure, rho is the density of the fluid, and that this is the velocity and also static pressure at any point dekat tube tu lah. So at the stagnation point, actually the velocity fluid is zero. Yang ni macam kita cakap tadi lah kan. where the at the stagnation point, the fluid flow will brought to rest, in which velocity will be equal to 0. And but if the gravity head, ini ada additional terms, gravity head of the fluid at a particular point in the fluid is 0, then the stagnation pressure at a particular point is equal to the total pressure. And bila kita consider tak ada gravity head, P stagnation ataupun P0 ni is equals to the total pressure. But however, in general, total pressure will differs from stagnation pressure, in that total pressure is actually equals to the sum of stagnation pressure and gravity head. Okay, actually dia kena consider gravity head sekali untuk total pressure. Tapi if let's say gravity head is not to be considered, kita boleh consider P total is equals to the stagnation pressure. Okay, and this is just an additional notes for compressible flow, meaning fluid flow yang boleh decompress. The stagnation pressure is actually equal to the static pressure only if the fluid entering the stagnation point is brought to rest isentropically. Okay, so this part is a bit different lah. And if let's say the flow is considered compressible. Okay, kita continue. Okay, so basically we have learned about the theory, the how to use the Bernoulli equations and what it is all about. Okay, so from this part onwards, kita akan lebih kepada application, how to apply those equations that we have learned, both the continuity and Bernoulli equations. So for this part, kita akan assess for a flow through an orifice, di mana kita akan consider this Bernoulli equation lah. Okay, so first of all, what is an orifice? An orifice is actually a small aperture through which the fluid passes. As we can see from this figure, this is an orifice. Orifice dia macam satu plate je, yang mana dia bentuk dia macam ni lah. And the thickness of an orifice in the direction of flow is very small in comparison to its other dimensions. It means that dia punya this width ni small je comparison to dia punya height. Okay, dia sikit je, kan? Dia adalah satu structure yang mana dia akan create satu aperture through which this fluid or gas flow will pass through. Okay, contoh, if a tank containing a liquid has a hole made on the side or base through which liquid flows, then such a hole may be termed as an orifice. So means that macam kalau satu tank tu kan, tank tu if let's say dia ada hole kat sini ke, dia ada hole kat sini yang mana membolehkan liquid dalam tank ni untuk keluar, benda ni semua boleh dikatakan sebagai orifice. Okay, apa-apa yang membolehkan atau hole membolehkan this liquid to drain out and through the hole. Okay, the rate of flow of the liquid through such an orifice at a given time will depend partly on the shape, size and form of the orifice itself. So ini logik lah, kan? Apa-apa shape lubang ni atau lubang ni akan mempengaruhi rate of flow yang keluar. Okay, shape sama ada dari bentuk shape dia, size dia ataupun dalam bentuk form dia. Okay, so an orifice usually has a sharp edge, kan? Usually it will have a sharp edge kalau kita tengok contoh ni, kan? Okay, so that there is a minimum contact with the fluid and consequently minimum frictional resistance at the sides of the orifice. So kita fikir logik lah. Contoh yang ni orifice, kan? Okay, so dia kata kat sini orifice ni selalunya dia ada sharp edge benda ni, supaya dia ada minimum contact dengan flow yang nak keluar tu. So flow yang nak keluar tu hanya bertemu di tip of the orifice sahaja. If let's say bentuk dia macam ni, So dia akan ada banyak lah frictional resistance dekat area sini. So dia akan reflect rate of flow yang akan keluar daripada this hole ataupun this orifice. Okay, if a sharp edge is not provided, ni dia cakap if let's say this is not happening, the flow depends on the thickness of the orifice and the roughness of its boundary surface too. So maksudnya dia bergantung pada thickness. So maksudnya benda ni lagi thick, lagi banyak lah friction loss, and then roughness ataupun material dekat orifice ni lah akan effects on the rate of flow of the liquid yang akan keluar. Okay, yang ni kita consider satu case mana flow from orifice at the side of a tank. So maksudnya yang ni dekat side ni maksudnya satu tank kan, dia consider kalau flow tu keluar dekat side. So the liquid issues from the orifice as a free jet under the influence of gravity only. Okay, yang keluar ni ada influence by the gravity only. The streamlines approaching the orifice converge toward it. So maksud dia flow yang dalam tank ni semua akan converge untuk dia keluar. Okay, keluar towards the orifice. Since an instantaneous change of direction is not possible, the streamline continue to converge beyond the orifice until they become parallel at section CC. Maksud dia akan keep continue selepas dia keluar daripada orifice section ni, dia akan continue to converge, and then dia akan dalam bentuk parallel. Maksud dia sama untuk flow yang keluar tu dekat area CC ni. Ini area CC ataupun dengan nama lain, benda ni sebenarnya kita panggil sebagai vena contracta. Okay, take note this is a vena contracta di mana streamlines is converge and then the flow becomes parallel. Okay, for an ideal fluid, streamlines will strictly be parallel at an infinite distance. So if let's say fluid ni ideal, dia akan keep on bentuk dia parallel lah at an infinite distance. But however, fluid friction is in practice produce parallel flow at only a short distance from the orifice. So kita fikir under the influence of gravity, confirm lah dia akan jatuh ke bawah. So dia hanya akan ada sampai satu area sahaja yang mana dia akan jadi parallel, and the area of the jet at section CC is lower than the area of the orifice. Kalau kita tengok sini kan, sekejap saya padam balik. Area sini, area at this CC section and also area at the orifice is different. Dia mesti, this one is much lower than this one. Okay, and this one macam again, it is called a vena contracta. Okay, so what is a vena contracta? It is the point in a fluid stream where the diameter of the stream is the least. Okay, kalau kita tengok dekat gambar ni gambar kita tengok gambar tadi okay, sekejap saya padam semula. Betul tak? Diameter dia adalah paling kurang kan, dia paling kecil kat sini kan. Kat sini kan semua besar, lepas tu dia converge kat sini, lepas tu dia besar balik, ataupun bentuk ikutlah bentuk macam mana. Tapi this vena contracta will give the lowest the least diameter lah of the stream, and fluid velocity is actually at its maximum point at this vena contracta point, such as in the case of a stream issuing out of nozzle. Contoh yang ni sini memang area dia paling kecil, tapi dia punya velocity is at its maximum value. So how kita calculate this vena contracta? So kita boleh refer to this coefficient of contraction. Coefficient of contraction di mana kita compare sama ada in term of area ataupun in term of diameter. So in term of area sama ada A area at the vena contracta divided by area at the orifice, ataupun in bracket diameter at vena contracta over diameter at the orifice squared. Okay, this is how we calculate the coefficient of contraction in which we will define the vena contracta lah. Kalau kita tengok dekat sini kan, this is the value of a vena contracta. If let's say the orifice punya shape macam ni, if let's say bentuk dia macam ni, this is the value, and bentuk dia macam ni, this is the value, and bentuk dia macam ni, this is the value. So ini berbalik kepada asal ni lah. The rate of flow of the fluid liquid through such an orifice will depend partly on the shape, size and form of the orifice. Okay. Okay, this is another example lah. The contraction of the jet actually can be attributed to the action of a lateral force. Lateral force on the jet due to the change in direction of flow velocity when the fluid approaches the orifice. Kan bila fluid approaches the orifice, dia akan bergerak dari semua direction. Semua nak berebut-rebut nak keluar kan. Since the streamlines become parallel at the vena contracta, which is this one, this is the vena contracta, the pressure at this section is assumed to be uniform. Okay, pressure at this section is considered to be uniform, velocity is at its highest, and its diameter is at its lowest. So this is the characteristic at vena contracta. Okay, so if the pressure difference due to the surface tension is neglected, the pressure in the jet at vena contracta becomes equal to the ambient surrounding jet. So means that kalau kat sini kita consider ada 2 point lah. Satu point dekat atas ni, satu point dekat luar. Dekat keluar ni lah, dia keluar daripada orifice. So dia kata apa? If the pressure difference due to the surface tension is neglected, the pressure in the jet, maksudnya dekat bawah ni, kat luar ni becomes equal to that ambience surrounding the jet. So maksudnya dekat sini dia akan jadi atmospheric pressure. So that is why dekat P2 ni dia jadi atmospheric pressure, and that is why based on Bernoulli, between point 1 and point 2, dekat P2 kita replace by atmospheric pressure. Okay, considering the flow to be steady and frictionless, frictional effects to be negligible, means that frictionless, we can write the application of Bernoulli between point 1 and point 2 like this. With point 2 ni actually dekat vena contracta lah, macam dia mention kat sini. Okay, and the horizontal plane through the center of the orifice, so meaning yang ni lah, horizontal plane through the center of the orifice has been taken as a datum level for determining the potential head. Potential head ni adalah H lah, ketinggian ni. If the area of the tank is large enough as compared to that of the orifice, the velocity at point 1 becomes negligibly small, and pressure P1 equals to the hydrostatic pressure at that point as P1 equals to atmospheric plus rho GH. So apa dia nak cakap kat sini, if let's say area of tank, okay, sangat besar as compared to this area, so kita boleh consider velocity dekat point 1 ni very very small ataupun sama dengan zero kan. Kalau kita fikir logik lah, kat sini memang seolah-olah tak bergerak sebab dia besar sangat, tapi kat sini dia sangat laju. So differences dia sangat besar, so kita boleh assume V1 is negligible ataupun V1 equals to 0, and also kat sini 0, P1 dia equals to atmospheric pressure yang dikenakan dengan rho GH. Rho GH sebab ketinggian dia lah. Okay. So itu yang kita kena tahulah. So kita tahu kita nak kena replace ni dengan ini, dan kita actually since V1 is negligible, this item will be 0. Okay. So sebenarnya saya dah tunjuk lah dekat sini. So tak apa, saya tunjuk sekali lagi. Sorry batuk sikit. Okay. So yang ni equation yang diberi tadi, kita dah ganti P2 dengan atmospheric pressure, and then V1, since V1 is negligible, this term will be 0, and then we substitute this P1 dengan this value. So bila kita substitute, atmospheric pressure plus rho G H minus Z1 over rho G plus Z1 equals to PATM over rho G plus V2 squared over 2G. And okay, so this one plus 0. Okay, dia consider plus 0 dekat V dekat sorry, saya lupa nak mention tadi, Z2 is actually 0 lah, sebab kita consider apa tadi, datum dia dekat sini. So untuk kira potential head dia, start dari datum ni. So this point onwards ke atas baru ada value. So meaning Z2 dia start from 0 lah. That's why Z2 is 0. Okay. So this one is 0. Okay, so kita dah ganti, kita akan dapat benda ni lah. Okay, so since bila kita balancekan kiri and kanan, this item and this item can be cancel out, and then minus Z1 and Z1 cancel out. So what is left is H equals to V2 squared over 2G, and then kita rearrange, kita akan dapat V2 is actually square root of 2GH. Kan? So kat sini dia mention that the velocity with which a jet of liquid escape from a small orifice is actually proportional to the square root of the head above the orifice. Kan? V2 ni actually proportional to the square root of head, this H value. Okay. And this is actually known as Torricelli's formula. Okay. However, yang ni if let's say kita consider ideal fluid, no friction, frictionless, inviscous, inviscid. Okay. However, if we consider velocity V2 with some frictional effects, kita kena consider multiplying by a factor of CV. CV ni adalah coefficient of velocity which is introduced to determine the actual velocity. So yang ni adalah tadi adalah ideal velocity, but this one is actually actual velocity. So kita benda ni pun kita fikir logik lah, kita tambah ni supaya kita nak reducekan value of V, sebab value of coefficient is actually 1 and below. So bila dia less than 1, total velocity akan kurang. So macam mana pun V ideal must be greater than V actual. Okay, V actual ni akan macam mana pun kurang daripada V ideal disebabkan the introduction of coefficient of velocity ni, yang disebabkan ada friction pada fluid tu, yang dikenakan pada fluid tu. Okay. Okay, next, since the role of friction is to reduce the velocity, kan, faham kan, bila ada friction dia akan reduce velocity. CV is always less than unity. Okay, yang ni macam saya cakap tadi lah, CV will always be less than 1. And the rate of discharge through the orifice can be written as A times V. Okay, yang ni kena tahu. Rate of discharge is Q equals to A times V. A is area dekat mana dia keluar tu, and V is V velocity dekat mana yang dia keluar lah. And so kat sini kita ada apa, introduce AC as the cross sectional area of the jet at vena contracta. So this part is actually V, and then this one is A. This is how you calculate the rate of discharge. Okay, and defining a coefficient of contraction, CC, macam yang saya mention tadi kan, coefficient of contraction as the ratio of the area of vena contracta to the an orifice, AC over AO, and at contracta over at orifice, kita boleh written as kita ganti this area of cross sectional area at vena contracta dengan CCAO kan, CCAO kita ganti ini dengan ini, sama je basically, kita just replace lah, where AO is the cross sectional area of the orifice. This will depends on what you will provided in the questions kan, yang mana yang boleh, kita boleh tukar-tukar bergantung kepada keperluan soalan. Okay, so the product of CC and CV is actually CD, which is the coefficient of discharge. Okay, kita tahu CC is coefficient of contraction, and then CV is coefficient of velocity. So the product of these two coefficient will give you the coefficient of discharge. So actually these terms we can replace with coefficient of discharge, yang mana kita akan dapat yang ni lah. Okay, so kita dah dapat ni, actually kita boleh dah calculate the coefficient discharge in which equals to Q over A naught square root of 2GH, yang mana the Q is actually the actual discharge, and those yang belah bawah ni adalah the ideal discharge. Actual discharge is those yang kita consider all the frictions, and the ideal if let's say all the frictionless. Okay kan, ini pun kita boleh fikir secara logik lah, yang mana kita akan dapatkan value of coefficient of discharge. Okay, so kita pergi kepada satu contoh soalan lah. Okay, soalan ni apa dia tanya, estimate the time it takes to drain 4 cm diameter manhole inside the diameter that is filled with 2 meter of water through a 2 mm drain hole at the bottom. So apa yang diberi, ini adalah 2 mm diameter, ini adalah 4 cm diameter, and then kita ada 2 meter water. Okay, so yang dia tanya estimate the time it takes to drain a 4 cm diameter manhole. So maksud dia, this liquid berapa masa diperlukan untuk kita drain, untuk kita keringkan, keluarkan through orifice kat bawah ni kan, berapa masa dia. So bila kita kata T, mesti kita akan kena mengena dengan rate of discharge. Okay, rate of discharge adalah dB over dt. Okay, yang ni tak apa, yang ni jap kita go through Okay, so solution, macam mana kita nak selesaikan? Kita akan apply, biasalah kita akan apply this Bernoulli equations, and assuming that the velocity at the top of the water is close to 0 and therefore is negligible. Dia sama juga konsep macam tadi, since area dekat atas ni kan, dengan when compared to area dekat sini sangat besar, so kita boleh consider velocity dekat point 1 ni equals to 0, sebab velocity kat bawah ni sangat laju kan. So perbezaan dia terlampau jauh, That's why kita assume V1 equals to 0 or negligible lah. So apa kita boleh buat? Kita apply the concept of Bernoulli. Okay, Bernoulli, saya tulis balik lah. E1 over rho G. Rho G is this specific gravity lah, sama maksud dia, plus V1 square over 2G plus Z1 equal to P2 over rho G plus V2 squared over 2G plus Z2. Since V1 equals to 0, these items kita let go, kan? And then P1 and P2 are both atmospheric. So since P1 and P2 are both atmospheric, kita kena cancel out these two part. Okay, so what's left is Z1 minus Z2 equals to V2 squared over 2G. And then since Z1 and Z2 actually the value of H lah, since dekat sini adalah Z2, sini Z1, so this tinggi is actually kita consider H lah. Kita jangan substitute dua ni, kita leave it as H. So H equals to V2 squared over 2G, in which V2 equals to square root of 2GH. Okay, yang ni seperti macam mana kita dapat sebelum ni juga. So macam mana kita nak relate this velocity dengan rate of discharge? Macam saya cakap tadi, dV over dt adalah Q in minus Q out. However, rate of discharge untuk dia masuk tak ada, so dia consider Q1 equals to 0. Yang kita ada sekarang yang keluar ni Q2 equals to something, betul tak? Then since Q1 is 0, so yang ni 0, so dV over dt kita akan dapat equals to minus Q out. Okay, so from there actually kita boleh dapatkan this value Q out dulu sebelum kita nak dapatkan dV dt ni. Sebab T sebenarnya ada dekat sini. Kita sekarang nak cari T ni, berapa time taken untuk the water to drain out from this manhole, kan? So apa kita buat? Kita tahu Q equals to AV, betul tak? So yang ni kita consider at point 2 lah, kan? Q out, kan? Dekat Q2 lah kiranya. So area dekat dia keluar ni, kita guna area of circle tu lah. Okay, kita guna pi r square times V2, di mana untuk case ni diberi diameter dia equals to 2mm, kan? So tapi kat sini radius, so tak apa. Since dia adalah milimeter, kita kena darab 2 kali 10 kuasa negatif 3 divided by 2, sebab kita nak radius squared V2. And then this will give 3.142 times 10 to the power of minus 6. Okay, and then V2 ni kita dah tahu tadi apa? V2 equals to square root of 2GH. Kita replace square root of 2GH kat sini. Okay, so kita proceed dengan value G kita tahu, kan? So 3.142 kali 10 kuasa negatif 6 square root of 2 times 9.81 gravity, and then kita ada H kat sini. So this will give 1.392 times 10 to the power of minus 5 H. Okay, so kita boleh gerak sampai sini je. Sebab H tu kita tak tahu. Sebab H ni tengah bergerak ni, memanglah tinggi dia 2 meter, tapi H ni actually tengah bergerak, dia nak habiskan. So dia berbeza ikut masa. Okay, so kita nak tahu nanti bila H equals to 0, berapa time dia kan. So apa kita buat, kita tahu daripada sini tadi dia kata apa, dv over dt equals to minus q out kan. So dv over dt is actually minus q out, ataupun sama dengan minus yang kita dapat ni tadi lah, 1.392 times 10 to the power of minus 5 set H. Okay, ni kita tahu one part. Okay, next kita kena dapatkan dekat atas ni pula. Tadi kita guna apa, dekat dekat sini kan. Okay, so sekarang kita nak tahu this value kan, dv ni macam mana kita nak dapatkan value of v. Sebab yang ni dalam bentuk differentiation kan. So kita firstly kita kira dulu volume this apa, macam mana kita nak kira volume dalam this main hole ni. Kita tahu volume sama dengan apa, area kali H kan. Area bulat ni apa, this circumference ni times the height. Okay, area equals to pi r squared, sama macam tadi, and then times H, and then since the diameter given adalah berapa tadi, 4 cm, so kiranya 4 kali 10 kuasa negatif 2 lah, tapi divided by 2 lah, sebab R yang given is diameter H. So this one will give 1.257 times 10 to the power of minus 3 H. Okay, 10 to the power of minus 3 H. Lepas tu kita ambil balik ni tadi. Okay, since kita nak dv over dt kan, perbezaan of this volume over time. So since kita differentiate left hand side with time, on the right hand side pun kita kena differentiate over time, kali 10 kuasa negatif 3 dh over dt. Nampak tak kan, macam mana kita nak relate balik dengan this kita dah dapat the right hand side, macam mana kita nak dapat the left hand side. The left hand side kita dapat through sini yang ni yang belah right hand side dia. Right hand side kita dah dapat macam ni, left hand side dia kita kena dapatkan bentuk macam ni. So apa yang kita boleh buat, kita guna konsep of macam mana kita nak dapat volume dia. So nak dapat volume dia, kita replace, lepas tu kita differentiate with dt on both left and right. So kita samakan, so yang ni dah dapat equation kedua. So kita samakan equation pertama dengan equation kedua, sebab dv dt equals to minus q out kan. So dv dt actually 1.257 times 10 to the power of minus 3 dh over dt is equivalent to this one, minus q out ni kan, minus 1.392 times 10 to the power of minus 5 square root of h kan. So kita dah dapat yang ni, kita samakan yang ni dengan yang ni, sebab kita tahu dv dt adalah yang ni. Sekejap, saya colourkan sikit. Ni adalah dv dt, which is this part, and then yang ni adalah q out dia kan, this one. So kita samakan ini dengan ini untuk kita proceed dengan next step. So kita dah samakan. Sekejap saya tulis balik lah. Left hand side dengan right hand side tadi adalah, okay, that one 1.257 times 10 to the power of minus 3 dh over dt. Sorry ya, tulisan tak elok sangat, asalkan nampak equals to 392 times 10 to the power of minus 5 ZH. Okay, so apa kita nak cari sebenarnya? Kita nak cari time kan. So kita bawa dt kat kiri. So sekejap, saya rasa better kalau okay, saya bawa dt ke kanan lah kan, naik ke atas. dt equals to 1.257 times 10 to the power of minus 3 dh, okay, over minus 1.392 times 10 to the power of minus 5 ZH. Okay, and dt would be, kita selesaikan yang ni, kita akan dapat actually equivalent to minus 90.3 over ZH dh. Yang ni nanti minta semua try lah, kira kalkulator. So dia akan dapat ini bila kita selesaikan dalam ni. Okay, so now apa kita nak kena buat? Kita nak dapat t kan. So dari differentiation kita nak dapatkan t, kita kena integrate. So nak integrate kita kena buat macam mana? Kita just integrate. Kalau integrate belah kanan, kita kena integrate belah kiri jugalah. Belah kiri ni kita integrate minus 90.3 over ZH dh. Daripada mana? Daripada H tu kosong ke tinggi dia lah, ke H. Okay, dan bila kita integrate baru kita dapat T is actually equals to, bila kita integrate, kita yang ni integration lah. Hopefully you guys still remember negative 90.3 H ni square root of H, kita bawa naik atas, kita dapat H minus 1 over 2. But since we integrate, kita plus 1, lepas tu over, ambil yang atas ni minus 1 over 2 plus 1. Okay, yang ni semua kita integrate dari H ke 0 kan. Hopefully you guys still remember how to integrate. And then we continue. T is equal to minus 90.3 ZH. Tak apa, ini H was 1/2 jugalah. And since minus 1/2 tambah 1 adalah equivalent to 1/2 plus 1 is actually equals to H 1/2 ataupun ZH. That's why kita dapat ZH kat sini over 1 over 2 bila kita selesaikan yang bawah ni Alright, so daripada H ke 0. Okay, and then kita selesaikan yang ni, kita akan dapat minus 180.6 ZH daripada H ke 0. Okay, so bila kita replace H, kalau 0 habis terus lah. So dia akan dapat, kita akan dapat minus 180.6 ZH plus constant. Dan bila kita ada integration, kita ada tambah constant kat situ. Okay, next, sekarang kita dah dapat dah macam mana kita nak dapatkan T tu kan, time tu. Kita dah dapat satu equation yang mana kita boleh guna untuk find the value of T. But first of all, apa kita kena buat? Kita kena cari this constant. And how to find this constant? Kita replace at T equals to 0. maksud dia if let's say T equals to 0, time equals to 0, air dalam manhole ni dia tak keluar lagi kan, tak ada yang keluar lagi. Maksudnya kita baru nak mula. So bila baru nak mula, H dia berapa tadi? Diberi H equals to 2 meter kan. So when T equals to 0, H is actually equals to 2 meter. So kita replace lah. 0 equals to negative 180.6 square root of 2 plus C. So C kita akan dapat berapa? 255.4. So this equation akan jadi T equals to minus 180.6 H plus C. C kita dah dapat kan, plus 255.4. ok, kita dah dapat complete equation untuk find time kan. So maksud dia sekarang with this information kita boleh dapatkan masa pada kedudukan H bila pun tak apa. Tapi kat question ni dia tanya apa? Estimate the time it takes to drain. Maksud dia untuk keringkan this manhole. Untuk keringkan manhole, apa akan jadi pada this fluid level, water level ni akan jadi 0. Betul tak? H akan jadi 0. T sama dengan berapa? Bila H ni 0, bila dia dah drain. So kita untuk find time at H equals to 0. So apa kita buat? T equals to, bila this part is 0, T akan jadi 255.4 second. Betul tak? Sebab H kita substitute 0. So this part will become 0, and then what left over is T equals to 255.4 second. So this is the answer apabila dia tanya time for it to drain. Okay, itu sahaja untuk example kan. Example nampak simple, tapi jalan pengiraan dia agak mencabar sikit lah. Hopefully you guys can understand. Okay, kita continue with some other application of Bernoulli equations, and for this time around kita akan tengok macam mana penggunaan this Bernoulli dalam pitot tube, venturi meter and also orifice meter. So actually the determination of flow rate Q from the measurement of pressure drop depends straightforward kepada this Bernoulli equation. So macam kita nampak this Bernoulli equations is very much important untuk kita calculate all those flow rates, velocity and also pressure drop. Okay, so firstly kita akan consider pitot tube lah. Actually this pitot tube pun saya dah explain sebelum ni. Tak apa, kita tengok balik what is pitot tube. So principle of flow measurement by pitot tube was actually adopted by this scientist Henry Pitot in 1732 untuk measure velocity dalam river. Okay, so one end of the tube faces the flow while the other end is open to atmosphere as shown in this figure. So one part is inside the water kan. So dia akan faces the flow, fluid flow, and then the other side will be open to the atmosphere. So how does it works? So the liquid will flows up the tube when equilibrium is attained. So macam kita nampak dekat sini akan ada fluid yang naik kan, and the liquid reaches a height above the free surface of the water stream kan. Dia akan lebih tinggi daripada free surface of the water stream. And since the static pressure under this situation is equal to the
hydrostatic pressure due to its depth below the free surface, the difference in level between liquid in the glass tube and the free surface becomes the measure of dynamic pressure, and therefore we can write by neglecting friction. Biasalah untuk Bernoulli usually kita akan neglect friction. P naught minus P equals to rho V square over 2 equals to rho GH. Okay, where yang ni P naught adalah stagnation pressure. Okay, P adalah static pressure. Okay, and this rho V square over 2 actually adalah second term dalam Bernoulli equation. Ingat lagi tak Bernoulli equation? Bernoulli equation apa? P over rho G kan, plus rho V squared over 2 plus ZG equals to constant kan. So untuk dynamic pressure kita hanya consider this part. Okay, seperti yang saya cakap sebelum ni kan, bila kita cakap pasal pitot tube is actually more on total pressure. Okay, total pressure is actually equals to apa? P static plus P dynamic. Betul tak? Okay, so P static is there, however the P dynamic is actually equivalent to P stagnation at this case. Okay, that is why kalau kat sini kita guna P naught minus P equals to rho V square over 2 equals to rho GH. Okay, whereby bila kita equatekan this term dengan this term, kita akan dapat inilah kan, rho V square over 2 equals to rho GH, and then kita dapat V equals to square root of 2GH. Okay, alright. So this such a tube is known as a pitot tube and provide one of the most accurate means of measuring the fluid velocity lah. Kita nak dapatkan velocity dekat sini kan. So this figure A is actually a tube for measuring the stagnation pressure. Okay, for measuring the stagnation pressure kita guna this pitot tube, and in order to calculate total pressure, in which is the static pressure plus the stagnation pressure macam saya mention dekat sini total pressure dia, kita kena guna both. This one ingat lagi tak apa? This one is piezometer untuk dapatkan the static pressure, and also this pitot tube untuk dapatkan the dynamic pressure. Sorry, P dynamic Okay, so kalau kita tengok dekat sini kan macam saya cakap tadi kan, this the second terms in Bernoulli which is kita consider untuk pitot tube adalah dynamic pressure. That is why kita consider yang ni sahaja kan, untuk dapatkan dynamic pressure. So that is why kita equatekan kat sini rho V squared over 2 sahaja, kita tak consider yang ni. Okay, so kalau kita nak consider both macam static pressure, sebenarnya kita guna macam saya cakap tadi, guna piezometer. That is why kenaikan daripada elevation from here to here actually the first term dalam Bernoulli equation kan, which is this one. This is the static and this is the dynamic Okay, so static. So kalau kita guna apa this pitot tube, kita akan dapat the stagnation pressure lah, ataupun the dynamic pressure kan. Okay, so clear perbezaan A and B. Cumanya A kita hanya ada pitot tube, yang mana kita hanya check the stagnation pressure. And the second part is bila kita combine both, kita ada piezometer, kita ada pitot tube, yang mana kita akan dapatkan the value of static pressure and also stagnation pressure, ataupun dia punya dynamic pressure lah kiranya. Okay. And for yang ni dia ada macam dia combine actually, kan macam pitot tube tadi hanya kepada stagnation pressure, tapi bila dia create di satu pitot static tube supaya dalam satu device dia boleh measure dua-dua sekali, kan. So kita baca sikit apa dia cakap kat sini. For an open stream of liquid via free surface, this single tube is sufficient to determine the velocity. Okay, this single tube sahaja so maksudnya this pitot static tube sahaja. But for a fluid flowing through a closed duct, yang ni open stream kalau flowing through a closed duct, the pitot tube measures only the stagnation pressure. Okay, contohnya macam ni kalau dekat sini closed duct, the pitot tube boleh kira stagnation pressure je. So the static pressure must be measure separately. That's why kita ada piezometer, kan. So in order to overcome this, they create this pitot static tube, yang mana both function of measuring the P static dengan P dynamic dapat dikira. Okay, so a pitot tube is also inserted as shown in 4.9 to sense the stagnation pressure. So yang ni actually the next slide tau gambar dia. This is the pitot static tube. Okay, kalau kita nampak gambar kat sini, it is a bit different lah. Dia ada combination of both piezometer and pitot tube, yang mana dinamakan pitot static tube. Kita baca dulu definition dia dekat slide sebelumnya. A pitot tube is also inserted, okay, to sense the stagnation pressure. The end of pitot tube measuring the stagnation pressure and the piezometric tube measuring the static pressure may be connected to a suitable differential manometer for the determination of flow velocity and the flow rate. So they combine both So terhasil lah this pitot static tube, in which the tube recording both static and stagnation pressure and combine into one instrument. Okay, this pitot static tube, and this tube sense the static pressure is known as a static tube, which surrounds the pitot tube that measures the stagnation pressure. Okay, so kalau nak ikut dia, sebenarnya dekat kawasan ni lah, kawasan ni dia akan dapatkan P static dia, dan kawasan ni macam biasalah dia akan dapat P stagnation dia ataupun P dynamic dia So this one static, this one stagnation dia, yang mana dia combine both function dalam satu instrument. Okay, so dari segi equation yang digunakan pakai, standard dia sama je, sama sahaja macam sebelum ni. Jap saya tunjuk balik waktu kita belajar pasal pitot tube tu. Yes, this one, kan. In order to find the velocity, kita guna this equation, kan. V equals to square root of 2 in bracket P stagnation minus P static over rho, kan. So the equation is similar juga untuk this case, okay, whereby this delta P is stagnation pressure minus P which is the static pressure. Okay. And kita ada tambahan kat sini factor C if let's say the fluid is not non-ideal, kan, due to friction lah, biasa, in which dia akan convert this dynamic head into pressure head, and to large extent on the geometry of the pitot tube. And kalau dekat in the instrument itself, C is usually determined from calibration test of the pitot tube. so this equation should be, you guys dah familiar lah. The concept is similar, cumanya digabungkan lah pitot static tube, combination of both function in the one instrument. Okay, so macam biasa kita buat example lah untuk memahamkan lagi kita punya konsep So this is related to pitot tube. Okay, a pitot tube is inserted in an airflow, yang ni dia punya density airflow tu 1.23 kg per meter cube, and to measure the flow speed, untuk flow speed dekat sini the tube is inserted so that it points upstream into the flow, and the pressure sensed by the tube is the stagnation pressure. Kan, kalau kita kata pitot tube adalah stagnation pressure lah kan, and P stat. Okay, the static pressure is measured at the same location in the flow using a wall pressure tab. So this one to measure the P static, and this one is used, the pitot tube is used to measure the P stagnation. If the pressure difference is 30 mm of mercury, okay, so this is the pressure difference, perbezaan ketinggian dia. Okay, determine the flow speed, kan? So apa dia nak suruh kira? Dia nak suruh kira the flow speed, kan? So how to solve these equations, this question, sorry. Okay, so firstly assumption, biasalah assumption Bernoulli yang kita kena take note. The flow must be steady flow, must be incompressible, and flow along a streamline, and also inviscous, inviscid. So meaning dia adalah frictionless, mana viscous effect is it not. Okay, yang ni benda penting kena take note these assumptions. So first of all, we need to write the Bernoulli equation along the stagnation streamline. Actually, kalau kita ingat lah, kita boleh guna rumus ni terus, kan? Which is this rumus, kan? Without C lah, sebab kita consider assumption tu. Yang ni if let's say non-ideal So actually benda ni pun can be derived from Bernoulli itself. Bernoulli is kita tahu P stagnation equals to P static plus this P dynamic, and then PO over rho G equals to P over rho G plus V square over 2G, and then G ni semua kita cancel out, dan kita dapat ni. Okay, P stagnation is actually at the tube opening where the speed has been reduced without friction to 0. Solving for V gives, so bila kita cakap macam ni, okay, so kita tukar kepada convert kepada this form untuk dapatkan velocity of the fluid, tapi kita selesaikan those inside dulu. Inside ni dulu, PO minus P, in which PO is rho GH, okay, untuk mercury, and also pressure which is equals to this one jugalah, okay, density time G H S Hg. Okay, sebab the flow okay, minta maaf ada masalah teknikal sikit tadi. So kita kat mana tadi berhenti? Okay, so sekejap saya padam balik dekat sini. So from here, from these equations, kita boleh convert kepada this equation balik lah. So macam saya cakap jugalah sebelum ni, if let's say kita dah ingat this equation, kita boleh guna terus lah kan, daripada this equation juga sebenarnya kan, delta P, in which delta P is equals to stagnation pressure minus the static pressure. Okay, so bila kita dah dapat this equation, kita kena selesaikan. Kita tahu this density of air berapa, kita nak dapatkan value of velocity of the air flow kan. So kita kena settlekan yang bahagian dalam ni dulu. Okay, P stagnation minus pressure. So ini juga dalam ni sebenarnya sama dengan rho GH kan. Kalau kita tengok ni, sekejap saya buka balik. Okay, so this one is actually the rho GH kan. So mana dia? This one. Okay, so this one is equal to rho dia, density of the mercury lah. Okay, GH. Okay, but since the density of mercury tak diberi kan. Kalau kita tengok soalan, density apa yang diberi? Kita hanya diberi Sg untuk mercury, and then kita diberi H untuk mercury kan. So apa kita buat? Actually kita tahu Sg equivalent to density of mercury over density of water kan. This is specific gravity Okay, so untuk dapatkan rho Hg, actually kita darabkan Hg with PH2O. That's why yang ni sebenarnya kita dah tukar kepada bentuk ini dan juga ini kan. This is given berapa tadi? 13.6, this one. So kita guna 13.6, H diberi 30 mm kan, 30 kali 10 kuasa negatif 3 kan, this one. Okay, and then G is 9.81 lah, and then density of water seperti yang kita tahu 1000 kg per meter cube and then kita dapat 4002.48 kan, the for the terms inside here, the stagnation pressure minus the static pressure, and then kita substitute masuk dalam this part. Okay, lepas tu kita darab 2 and then divided by density of air. Density of air pun given sebenarnya kan, berapa? 1.23 kg per meter cube, and then kita akan dapat the answer, which is the velocity of the airflow equivalent to 80.8 meter per second, in which sangat laju Okay, so kita pergi contoh lagi satu contoh yang, but this time around kita libatkan sama juga pitot tube with the piezometer. Okay, both instrument are tapped into a horizontal water pipe as shown in figure to measure the static and stagnation pressure lah. Yang ni guna untuk static, yang ni untuk stagnation lah. Okay, for the indicated water column height, determine the velocity at the center of the pipe. So kita nak tahu velocity dalam pipe ni. So kita kat sini kita ada V1, kita ada V2. So basically kita nak dapatkan V1 ni kan. Macam mana? Sebab kita tahu kat sini apa? Stagnation pressure kan. So by definition, stagnation pressure, velocity dekat stagnation pressure adalah 0. Sebab P max adalah P stagnation kan, based on konsep Bernoulli. Since pressure at its maximum, P stagnation, velocity must be at its lowest. So at this time kita consider V2 sama kosong, in which the fluid flow has come to a rest position. Okay, so bila dia kata velocity at the center of the pipe is actually this V1 dekat position 1. Okay, alright, saya padam balik kat sini. Okay, so macam mana kita nak dapatkan the velocity kat situ? So firstly, apa kita buat, kita dah tahu dua-dua yang ada kat sini ada piezometer dan juga pitot tube. Lepas tu kita dapatkan equation for both P1 and P2, kan? So kita tahu pressure equals to rho GH. Okay, so for piezometer, rho GH dia, rho GH in which H dia adalah H1 plus H2 lah, sebab ketinggian dia sampai sini kan. So this is the ketinggian H1 plus H2. Okay, so at position P2 pula adalah rho G apa, H1 plus H2 plus H3, and so dia ada 3 tu plus H3. So kalau kita nak tahu sebenarnya sini adalah P stat dia. Okay, static dia. Okay, so kita dapat kat sini P static equals to this and P stagnation equals to T. So noting that Z1 equals to Z2, so kita guna equation Bernoulli. Bernoulli kita tahu kan, yang ni bila kita samakan position 1 and position 2. So since Z1 and Z2 kan, ni position 1 and position 2, so dia tak ada elevation kan. So kita cancel out Z1 and Z2, and also V2 is 0 macam saya cakap tadi kan, dekat P stagnation sini V2 equals to 0. So dalam ni pun kita cancel out this term. So kita end up, kita dapat this equation. Okay, so and then kita replace P2 dengan P1 ni dengan apa yang kita dapat kat sini. Kita akan dapat ni, in which benda ni semua akan cancel out, and then benda ni pun akan cancel out. So yang kita tinggal adalah ini sahaja. Okay, actually yang kita tinggal adalah rho G H3 over rho G, kan? So this one pun cancel out, kita hanya tinggal dengan H3. So kita dah tahu sekarang V1 squared over 2G is actually equals to H3, and then kita boleh dapatkan this velocity V1 dengan kita rearrange untuk dapatkan the velocity at position 1, which is square root of 2G H3, and H3 is actually equivalent to 12 cm. 12 cm equals to 0.12 meter and then kita dapat the value of the velocity adalah velocity of the fluid flow dalam pipe ni equivalent to 1.53 meter per second. And kalau kita tengok kan, yang ni kecil pula kan. Yang sebelum ni, untuk case sebelum ni kita dapat airflow ni 80.8 meter per second. Maybe sebab the airflow kan, so laju. Tapi yang ni maybe dia ni adalah water, sebab water dia kurang laju sikit lah. That is why the velocity is much lower, 1.53 meter per second. And note that to determine the flow velocity, all we need is to measure the height of the excess fluid column in the pitot tube compared to the piezometer tube, kan? Apa yang kita buat, kita compare perbezaan ketinggian je, kan, in static tube dengan piezometer tube, yang mana kita dapat this value. Okay, itu sahaja untuk contoh for instrumen untuk pitot tube, ya. Kita dah settle this part. Okay, now kita proceed dengan the second instrument, yang mana kita akan apply this Bernoulli equation. Okay, the second instrument is the ventrimeter. Okay, so basically what is a ventrimeter? So this is the picture of a ventrimeter. So it's looks familiar, right? Asalnya kita pernah refer to this ventrimeter last time when we studied physics. Okay, a ventrimeter is essentially a short pipes consisting of two conical parts. Kalau kita tengok kat sini, dia ada this part is have a conical shapes, and also this part has a conical shape with a short portion dekat tengah-tengah ni, that is formed in between these two conical parts. And this short portion has actually the minimum area, and it is also known as the throat. The throat. The conical portion have the same base diameter. Kalau kita tengok kat sini kan, untuk kedua-dua ni diameter dia sama je, yang connecting the throat ni. Okay, but one is having a shorter length with a larger cone angle. Oh, kita tengok yang on the left sini, dia ada shorter length, tapi dia ada larger angle, larger cone angle. And the other one have much larger length, however with a smaller cone angle. Okay, this is what is it about the ventrimeter, and how does it working? Okay, so usually the ventrimeter is always used in a way that the upstream part of the flow takes place through the short conical portion. So sini is the upstream. Upstream akan selalunya akan lalu dari arah short conical portion, while the downstream part is the flow through the long one. Okay, dia bergerak from left to the right. Okay, why? Because this ensures a rapid converging passage. Kan kat sini dia akan rapid converging of the flow dekat sini, and a gradual diverging passage in the direction of flow, in order to avoid loss of energy due to separation. That is why the flow direction is from the short length of conical to the downstream dia dekat conical yang panjang. Okay, in course of a flow through the converging part, the velocity increases. Okay, so kat sini velocity increases terbalik. So dekat sini actually velocity increases, okay, in the direction of flow according to the principle of continuity with the pressure decrease. So macam kita belajar Bernoulli, velocity increase, pressure decrease. So on the other hand, dekat bahagian kanan ni velocity decrease but the pressure increase. And actually dekat tengah-tengah ni, the velocity will reach its max, okay, and pressure will reach its minimum point. Okay, and that is all about PV lah, the characteristic of P and V sepanjang ventrimeter ni. Okay, so as we can look at this picture, this ventrimeter is positioned in an inclined pipeline. Kan kita nampak dia sedikit incline as compared to the previous one. And let us consider flow yang lalu dalam this inclined pipeline atau ventrimeter ni as a steady, ideal and one dimensional. What will happen? Okay, so sekarang lebih kepada dia nak tunjuk macam mana how we derive equations to calculate flow rate if flow inside a ventrimeter lah. Okay, so first of all kita kena define dululah. So the position one is at the upstream. Okay, the second position is at the throat. Okay, so dekat sini kita ada V1, P1, and kat sini kita ada V2, P2 lah. Okay, so apa kita kena buat first? Based on Bernoulli, this is the equation. So equation ni dah familiar dah, saya rasa semua kan. So kita rearrange so that the velocity will be on the left hand side, where the density is actually the fluid flow through the ventrimeter, fluid yang flow dekat sini. So this is represent the density. Okay, and secondly kita juga kena apply the continuity. So based on continuity, volume flow rate on the upstream mesti sama dengan dekat downstream. So V1A1 must be equal to V2 and A2, where A1 and A2 are the cross sectional area of the ventrimeter at the inlet dengan at the throat. Okay, at the inlet dengan at the throat, A1 and A2. So kita dah dapat those two equation penting based on Bernoulli and based on continuity. Okay, next what we do from both equation, kita gabungkan. Okay, so daripada equation ni 4.y8 and 4.y9 ni kita gabungkan. So apa yang kita dapat from 4.y9 ni kita masukkan dalam 4.y8. Okay, so from 4.y9 kita tahu V1A1 equals to V2A2, and then kita ambil V1 equals to V2A2 over A1, and then kita replace this V1 inside this. This is 4.y8 tadilah. This is 4.19. Okay, kita replace, and then actually kita bila this is all mathematical punya procedure lah, kita akan dapat macam ni, and then kita akan dapat this part lah, macam ni. Alright, so dia akan jadi macam ni. So next kita dapatkan value of V2. V2 is equal to 1 over square root of 1 minus A2 square over A1 square square root of 2G. Actually on the right hand side kita convert this to this, because ada maksud dia, sebab kita nak create this one unknown H1 star and H2 star, in which this H1 star and H2 star are the piezometric pressure head, okay, at section 1 and at section 2 respectively, in which are defined as P1 over rho G plus Z1 for piezometric pressure head at section 1, and P2 over rho G plus Z2 as a piezometric pressure head at section 2. So basically dia sama je, dia just convert kepada bentuk ni supaya dia boleh relate dengan benda ni. Lepas tu benda ni dia ganti dengan H1 star and H2 star. Okay, so next, hence the volume flow rate through pipes can be given as, sebab kita tahu kan Q sama dengan AV. Okay, kalau kita tengok dekat sini kita dah dapat V2 kan. So nak dapat Q sama dengan A2 V2 lah kan. So kita darab A2 dekat sini, so dia dapat ni lah, kita darab A2 kat sini, kita tambah A2 kat sini. Okay, alright. So tak kisahlah bila kita kata volume flow rate, kan volume flow rate tak kisah sama kat sini, kita buat Q sama dengan A1 V1 ataupun A2 V2, sama je. So kalau kita nak guna yang ni pun tak ada masalah, cumanya dekat sini the example shows at section 2. Okay, so kita dah selesai one part based on Bernoulli and based on Bernoulli and based on continuity kita dapat this equation. Okay, so the second part kita kena consider this on the bottom side, which is the manometer. This manometer, and so if the pressure difference between section 1 and 2 is measured by a manometer shown, we can write. So ini ingat lagi tak? Okay, so kita ada dua part at section 1 and at section 2. At section 1 kita ada apa? Kita ada P1. Sekejap, yang ni saya padam dulu. Kita ada P1 plus ini ketinggian ni. So rho G delta H. Rho G Z minus H0. Z1 minus H0 untuk dapatkan this ketinggian. Okay, this ketinggian kan, Z1 minus H0. Okay, so that is on the left hand side. On the right hand side, apa kita ada? Kita ada firstly P2 lah, P2, and then kita ada this, kan? Yang tu adalah rho G Z2 minus delta H minus H naught, kan? Z2 minus delta H minus H naught. And then kita ada plus satu lagi, which is sampai sini, kan? Which is rho dia rho M lah, rho dalam manometer sebab tadi rho air flow dekat atas, yang ni dia jadi rho M delta Hg. Okay, so kita ada kat sini 1, 2, kat sini kita ada 1, 2, 3 part. So kita ada 1, 2, and then kat sini kita ada 1, 2, 3 part. Okay, so kalau kita tengok dekat sini, kita boleh cancel out this term because sama kiri kanan, and then kita rearrange, kita akan dapat something like this. Sebab apa dia nak dapatkan bentuk macam ni? Sebab kalau kita tengok benda ni ada kena-mengena dengan bentuk. Kejap, mana dia tadi? Okey, dengan bentuk ni P2 dengan over rho G dengan P1 over rho G. Okey, so tak apa, just kita susun dulu dalam bentuk ni. Okey, and then actually kita akan dapat kita dah tahu yang ni adalah equation tadi equation yang bawah ni tadi. Okey, so apa kita buat? Kita divide everything by rho G. Kita akan dapat this equation. Okey, kita akan dapat this equation, and then kita tahu ikut sebelum kalau kita bahagi rho G, kita akan dapat ni. This term is actually sama dengan yang tadi tu, which is the piezometric pressure head. Betul tak? Kan? H1 star dengan H2 star kita jumpa balik dekat sini. Ni H1 star, H2 star. So kita tahu H1 star minus H2 star sama dengan benda ni, kan? Where this is actually, macam saya cakap tadi, the density of the manometric liquid. Okay, so next okay, ni tak ada apa, so kita ke bawah through next slide. Okay, so bila kita dah tahu H1 dengan H2 adalah benda ni, kita replace balik dalam equation yang tadi tu. Kita replace dalam equation ni dengan what we get here. Okay, density rho M over rho minus 1 delta H. Okay, kita masuk dalam ni, and then on the bottom side kat sini actually kita boleh ringkaskan. Kita boleh simplify pada bentuk macam ni, and then kita akan dapat this. Jangan terkejut tiba-tiba dapat bentuk macam ni daripada benda ni. Actually kita boleh ringkaskan. This is all mathematical punya simplification lah. Okay, so nampak tak kita punya equation dah evolve kepada bentuk ni, kan? Sebelum ni bentuk dia macam ni, kan? So apa kita buat? Kita dah simplifykan bawah ni dan kita replace benda ni. Okay, dan kita dapat benda ni. Okay, so dia kata kat sini ni benda penting if the pipe along the ventrimeter is horizontal, kan sekarang disebabkan dia ada Z1 and Z2, disebabkan dia punya position ada elevation, kan? Point 1 and point 2 ni dia tak sama dalam satu line. Okay, but if let's say a pipeline along the ventrimeter is horizontal, then Z1 is equal to Z2. Betul tak? And hence H1 star minus H2 star will become H1 minus H2, kan? Sebab H1 star kan benda ni, H2 star kan benda ni. So if let's say Z1 and Z2 tak ada, and kita cancel out, dia hanya tinggal benda ni saja. Benda ni is actually, benda ni dah jadi H1, benda ni dah jadi H2, which is the static pressure at section 1, static pressure at section 2 kan. Kalau kita tengok Bernoulli, this is the first equation, the first term kan. The first term is actually the static pressure, which is H1 dan H2. Okay, so then the mathematical equations will then becomes like this kan. Sebab sebelumnya bentuk dia macam ni kan. So if let's say yang ni tak ada, dia akan jadi H1 minus H2 equals to this delta H. Okay. So apa yang nak diterangkan kat sini adalah it is interesting to note that the final expression of flow rate yang kita dapat tadi tu given by equation 4.24, which is this one, in terms of manometer deflection delta H remains the same irrespective of whether the pipeline along the venturimeter connection is horizontal or not. Okay, so means that kita boleh je guna equation ni if let's say venturimeter tu position macam mana pun tak apa. Tak kisahlah dia ada angle ke tak ada angle ke, dia horizontal ke dia vertical ke, kita boleh guna this equation. This equation apply to all. Mudah kan? So what you need to do is you need to know this equation je. Yang tadi tu semua lebih kurang derivation sahaja. And in the end, this is the equation that you need to know untuk kira flow rate dalam venturimeter. Okay, so ini biasalah they add on the multiplying factor CD dekat equation flow rate yang tadi tu. Okay, untuk if let's say kita consider the actual flow rate kan, dia kata Q actual. Okay, yang tadi ni adalah Q ideal lah, sebab kita consider no losses kan. But in the actual kita kena consider those frictions and so on kan. So by the addition of this factor, dia akan reduce the flow rate kan, sebab basically akan ada loss lah. So the coefficient of discharge itself is always less than unity lah. Ini macam biasa lah, kita tahu coefficient mesti less than 1. Okay, so ini sebenarnya adalah dari sini juga kan. Bila kita keluar, ini adalah Q actual, ini adalah tadi apa, Q ideal kan. So nak dapatkan CD is equals to Q actual over Q ideal lah kan. Q actual over Q ideal ataupun the theoretical. Okay, and also ada mention dekat sini, usually lah the value of CD for venturimeter lies between 0.95 to 0.98. So means that it's quite ideal jugalah this venturimeter, sebab CD dia agak tinggi, almost nak dekat unity lah kan. Okay, so kita go through an example of venturimeter, the venturimeter punya questions. Determine the flow rate, okay, flow rate through the venturimeter shown in figure below if ideal condition is exist. So ideal condition means kita tak payah consider the the coefficient of discharge tadi lah, sebab kita nak kira the ideal. Okay, so the condition is like this. This is the venturimeter, so this is the upstream lah. So this is position 1, this is position 2. Okay, given kalau kita tengok gambar ni, P1 diberi, P2 diberi. Okay, and also fluid punya specific gravity. So macam biasa, kita refer to Bernoulli equation, kita refer to continuity equation, and then kita dah dapat equation 1, kita dah dapat equation 2, and then since Z1 and Z2 pada position yang sama, kita consider 0, and then apa benda penting kita nak kena dapatkan adalah the fluid density. The fluid density kita dah boleh dapat daripada this specific gravity. So based on equation, specific gravity is equals to rho g, and then kita nak dapat rho, the density of this fluid, equals to Sg over gravity, in which kita boleh dapat 9 to 8 kg per meter cube. And then what we need to do is that we must put V2 ni ke dalam equation 1. V2 yang kita dapat ni masuk dalam equation 1. So kita replace. Saya tak perlulah tunjuk satu-satu kat dalam ni. Okay, and then kita akan dapat nilai V1 equals to 8.09 meter per second. And then this based on flow rate, kita dah tahu kan V1 kita dapat berapa, kita dapatkan value of A1 tadi macam mana saya cakap adalah cross sectional area dekat sini. So dia ada diameter of 31 mm, and so dia PR squared ataupun PD over 2 squared. Okay, so yang ni dia replace, dia dapat the flow rate equals to 6.103 times 10 to the power of minus 3 meter cube per second. Okay, and now we go to the last part, ataupun the last instrument, which is an orifice meter. Actually this orifice meter kita dah saya dah terangkan melalui flow over an orifice meter dalam slide awal sebenarnya. So dia konsep dia yang sama lah, cumanya penerangan ini lebih kepada in general how the use of orifice meter can be used to calculate the flow rate. Okay, so as for the construction, as can be seen kan, kalau ada orifice, this is an orifice. Orifice meter provides actually a much simpler and cheaper arrangement kan, as compared to macam yang sebelum ni kita ada venturi meter kan, in which dia ada two conical punya area, and then the throat, and then size of the venturi meter pun is a bit larger kan. So if let's say we use this orifice, kita hanya provide this area sahaja, okay, yang can be considered as an orifice, and that it is used to measure the flow through a pipes. Ni satu pipes, they just add on two pieces of this orifice in order to measure flow yang lalu through this pipe. And how does it works? So the orifice plate being fixed at a section of the pipe, macam yang kita lihat dalam gambar ni, creates an obstruction kan. Bila dia creates obstruction, the flow by providing an opening in the form of orifice to the flow passage. Bila dia create this obstruction, the flow will deteriorate. Okay, this deterioration ni lah yang kita akan gunakan on how to measure the flow inside for an orifice meter. Okay, so macam biasa bila kita kata orifice meter, dia ada vena contracta as I mentioned sebelum ni, which is this section sekejap, tak berapa clear pula kat sini. Okay, this section yang mana flow dia boleh kata uniform, this is vena contracta dia. Okay, so based on Bernoulli equations, kita ada benda ni. So yang beza dia adalah yang ni dekat position 1. Okay, this is position 1, this one before dia masuk ke orifice tu, this is position tu lah, ataupun position vena contracta ataupun C. Okay, so we replace P1, B1, PC and BC. So Z tak ada, term Z, Z1 and ZC tak ada lah, disebabkan dia tak ada elevation, dia straight line saja, horizontal kan. So the equation would be like this. And then this one is based on Bernoulli kan, based on Bernoulli theorem. And then biasalah bila kita buat bahagian flow measurement, kita kena consider juga continuity. Continuity means that apa yang lalu dekat sini sama juga dengan lalu kat sini. volume flow rate dekat sini sama dengan volume flow rate dekat bahagian sini. Okay, so kita ada V1 A1 equals to BC AC, where AC is the area of the vena contracta lah. And then we rearrange, we combine both 4.26 and 4.25 ni, kita akan dapat this VC. Okay, so hence macam mana kita nak calculate the volume flow rate? Q equals to AC BC, in which BC is this one, AC is the area of vena contracta lah. Usually will be given, okay, in terms of diameter ke radius ke, nanti kita convert lah. Okay, so that is all for this chapter.